you see the distribution. You see the sorry, I have to get this. Now we get that. So you see the distribution as a function of this initial arbitrary angle and the correlation to the mass displayed down here. Now we have a totally different situation if the Patzay-Quinn symmetry breaking energy scale is lower than the one of the inflationary energy scale. What happens then is that we first have inflation and then Patzay-Quinn symmetry breaking. So what we see in our universe today is actually made up out of many, many patches that all had arbitrary theta I values that were not in causal contact with each other, which means that we actually do have an average effective theta in place, which gives us now a prediction on the average theta, right? Now, this would be very nice and easy, which would give us a very exact prediction for the axion mass. Unfortunately, also this band is stretched quite a lot, because if we have this configuration, this means that we also are creating topological defects between the by relaxation of this theta I, which then decay in the later universe and lead to additional axion production. This is extremely difficult to calculate, and this is a big debate. However, there is consensus that in the post-inflationary universe, the mass of the axion should be something between, say, 25 microelectron volts up to 1 millielectron volt. Good. Now I gave you a quite long introduction of this post-inflationary scenario. Why is this so relevant? Well, we don't know which scenario is in place. And if you look at the current situation, the limits that are in place, you will see that all the cavity experiments are actually going up basically to the lower end of this post-inflationary scenario. So there is hardly any experiments available. 5 years ago, there was basically nothing yet that would be able to scan masses, axion masses above, well, say 40 microelectron volts. So the dielectric haloscope concept is really set out to change this and to specialize on achieving sensitivity in the mass range of the post-inflationary scenario. Now, how do we do that? Let's start with a basic idea, the so-called dish antenna concept. Now, we all know that the axion field, by inverse Primakov effect, if we have a B field, that static B field in which we have the axion field, this induces electric field oscillations. They're tiny, but they are being induced. Now, if we have two media, vacuum, for example, and medium with dielectric constant of 4 here in this example, well, to the axion field oscillation, this does not do anything. However, as we all know, the induced electric field will have different amplitudes in vacuum or in a dielectric medium, which means that all of a sudden at the interface of the two media, we have a discontinuity, which obviously is not allowed according to Maxwell's equations. So as an effect, what happens is that there will be emission of photons in both directions to compensate for the electric field discontinuity. You can all calculate that classically, and you will see, putting it the numbers, that the power that you expect, that the power that you expect is something like 2 × 10⁻27 watts per square meter of an ideal mirror here in a magnetic field of 10 Tesla strength, obviously depending on your coupling constant and the axion mass. Now this we can utilize. 10⁻27 watts per square meter are very, very low, of course, very, well, challenging to detect. So you want to boost that. So either you can increase the size of your mirror, or we can use the dielectric haloscope concept. So what you have here now as a concept is that you take such a mirror, such a dielectric dish, basically, and now stack many dielectric disks with a low tangent delta, with a low dielectric loss in front of this mirror. This does two things. First of all, now we don't only have emission from the mirror of the setup, but each transition will now additionally lead to coherent emission of photons. So in such a setup, we can use constructive interference of the coherent photon emission from all the surfaces at the dielectric layers and at the mirror. Now, if you have constructive interference, you can also generate a boost. And again, you can calculate that very classically. What we now define is the so-called boost factor, which we call beta squared, which is defined as the power emitted by, sorry, this should not read cavity, but power of the booster over the power of the single mirror. And this can be as high, using 1D simulations, that's rather easy to see. This can be as high as 10 to the 4, 10 to the 5. Right? For example, here you see a calculation of such a boost factor curve for different arrangements of the dielectric disks. Of course, the frequency where you will have the boost will depend on the distance between the dielectric disks. Now you can play around and change the distances, don't have them all equidistant, and then you can basically come up with broadband amplification of the axion to photon conversion. Right? And now what you see here, note this is beta, not beta squared. You can come up with either broadband emission, broadband amplification, or if you really make your disks equidistant, you can also tune this to very narrow band configuration, however, with a very high boost factor. So this allows you to optimize your boost scan strategy according to needs, of course, also according to mechanical feasibility. Now, this is the basic idea of the MADMAX experiment and the basic idea of such a dielectric haloscope. So what we would use here, what we want to do is to use exactly such a booster, as I just explained, a mirror with up to, say, 80 dielectric disks in front of this mirror, and put this into a large dipole magnet, say 9 Tesla with 1.35 meter bore, right? So inside this dipole magnet, within this booster, a power is generated from axion to photon conversion if we tune the dielectric booster to the right frequency of something like 10 to the minus 23, 10 to the minus 22 watt, which could then be deflected by a focusing mirror and then collected by antenna and then detected by a low noise detector and recorded by an according receiver chain. So this is the basic idea. Now let's try to put this into reality. Of course, we have a few challenges here. First of all, we obviously have the B field. You realize this is a dipole magnet with a bore of 1.35 Tesla with a B field of with a bore of 1.35 meters and a B field of 9 Tesla. This is a magnet which will have a huge stored energy of several hundred megajoules. Such a magnet has never been built before. So this is a challenge to start with. Second of all, obviously, we have to care about the booster, and we have to start understanding what kind of precision we need for the individual disks, for the disk placement, and so on. And we need a booster that not only gives us this precision, and accuracy and repeatability, but a booster that we can also tune. So each of the individual disks, we should be able to move. So that's another challenge. Then we all know detecting a signal of 10 to the minus 23 watts. You all are aware of Dicke's radiation formula. So we cannot allow for a high system temperature, which means that the whole system should actually be cooled down to liquid helium temperature, optimally even to lower temperatures. And then, last not least, we have signal detection. So in the end, again, back to Dicke's radiation formula, we will end up with a requirement that we want some kind of preamplifier at the first stage that is at least close to quantum limited. And this is actually the topic of this conference. This is not what I am an expert with, but this is what I want to become a user of in the very near future. And this is why I think it's nice if you, as experts in this field, see why we need this kind of detection technology that you are all developing. Okay, so the MADMAX collaboration was found in 2017 at DESI in Hamburg. We started that at Max Planck Institute in Munich. Now we have DESI in Hamburg that joined, and quite some other institutes that are around. The experiment is supposed to be located at DESI in the North Hall. You see actually the location, the proposed location for this for the experiment. We already have a yoke for the magnet. This is not the real magnet yet. This is the predecessor magnet from the H1 experiment, but this is the allocated space for us, where already actually the cryogenic infrastructure is being prepared. Okay, let me quickly go through the construction sites now. So we have a receiver chain, obviously, that is very important for detection. So what we have shown previously, Yannis has seen this before, is that actually with the conventional high electron mobility transistor from low noise factory with a liquid helium cooling, we already actually accomplished to measure a 10 to the minus 22 watt signal within something like 4 days. Be aware, this is without the booster. This was not a real axion. This was a fake axion. So we injected a fake axion signal into our low noise hand, and then took data for 4 days, got this background in the frequency range of 50 megahertz around the frequency of 18 gigahertz. And a blind analysis was performed, and indeed this signal could be blindly found by the people that had no idea where actually the frequency was that was injected. So obviously we're using heterodyne downmixing, but for us the important thing here now is the low noise amplifier at the input side, which here was operated in the helium bath. So that's all good, but we want to do better. Here we had a system temperature of 5 Kelvin. So what we are in parallel doing is the group around Nicolas Roche, you heard about him before in the presentations from Quarks. He has developed TWPAs, and he's also part of our MADMAX collaboration that are going above 10 gigahertz already. So TWPAs, traveling wave parametric amplifiers, they're extremely nice for us because they're broadband, as you all know. And what they showed in the group around Nicolas Roche at Neil is that even at 12 gigahertz, they get a gain of above 20 dB with a bandwidth of more than 1 gigahertz. And what you see here is basically the added noise as a function of frequency here up to 11 gigahertz, shown up to 11 gigahertz. This was taken with a pump frequency at 8 gigahertz. Sorry, I cannot show you the numbers now at with the pump frequency at 10 gigahertz. But what you see that now we're adding a noise of approximately 1 Kelvin, which reduces now our system temperature from the initially 8 to 10 Kelvin that we had with a hand to something like 5 Kelvin, which dramatically increases our potential scan speed. So now further activities are ongoing. First of all, we start at 10 gigahertz and want to go to higher frequencies. First up to 30 gigahertz, and then all the way up to 100 gigahertz. And Neil is presently looking into what needs to be done to accomplish such a TWPA for frequencies up to 20 gigahertz. And what they're doing is they try to further reduce the noise that is induced by dielectrics at higher frequencies. There seems to be quite some understanding. This is work in progress, and we are very curious and eager to see the results in the hopefully not so far future. A small word, what happens about 30 gigahertz? Well, there we do not really have a concept. This is basically still more or less open territory. However, there are many ideas, and well, you here on the conference are the experts to discuss what everything we could do to detect real photons above 30 gigahertz to 100 gigahertz. We heard about qubits. We know there are other possibilities, SIS mixes, transition edge sensors, but maybe also graphene detectors, or so on. So we're looking into many ideas here, but that's more or less still an open question, what to do above 30 gigahertz. Okay, my time is running away, so let me quickly go through the other challenges. I told you about the boost factor. What we did so far is look into idealized 1D world, and there everything looks very harmless. Obviously, the three-dimensional reality looks different. So we have to understand what actually all the inaccuracies are doing to our booster amplification, right? So for example, small tilts of the disks. Planarity, if it's not perfect, the disks are not perfectly planar, or if we have a surface roughness of the disks. Now note, these simulations have been done for an open booster without any kind of surrounding. But nevertheless, I think this is very important and intuitive to look into the effect of small tilts, small planarity variations, and surface roughnesses, just to estimate what we really need in practice. And you realize that things seem to be, well, challenging, but not impossible. And that's what we're working on. So a tilt of something like 100 micrometer per disk diameter does not deteriorate too much the boost factor. Similar thing for the planarity, 100 micrometer planarity is well, not nice, as you see here, but a planarity of many tens of some tens of micrometers might still work. Also, please note this is now here given in sigma and not the usual minimum maximum that usually is given by the mechanical engineers. And surface roughness, that at least does not seem to be too challenging. So as you see, yes, it's a challenge, but we are very optimistic that in the end we can do that. What we still have to do is now to show what happens actually to this system if we actually put it into a real surrounding with some arbitrary, not arbitrary, but boundary conditions, which include the holders for the disks and motors and everything around. This is work in progress. Okay, then you can look at the beam shape. I told you what we're looking at is basically a beam that is emerging from this booster. How is this now being varied by tilts, by thickness variation and the surface roughness? And you see with the parameters given up here, this all looks rather nice, comparing the Gaussian, basically ideal beam shape that for our antenna would be the best with respect to a beam shape that is produced by some tilts, arbitrary tilts, by thickness variations or surface roughnesses. Well, this all also looks quite nice. Okay, let's go quickly for the test of feasibility at all. The possibility of putting disks into the right distance. So what we have done here, again, this has been shown in earlier conferences. We have a setup in Munich that is heavily being used to understand and optimize positioning algorithm. Basically, what we do is we measure the reflectivity S11 of this booster setup, again using a focusing mirror, looking with a VNA into this thing, and then measuring reflectivity, which with a 1D simulation, we can translate into a boost factor that we have. So here we have a setup with which we can use up to 20 disks. We can position them and then make measurements. And this is what you see here. This all has been published already. Now with a few disks already, 4 or 5 disks, what you can do is you can go here actually from your group delay, calculate then your boost factor and see what the frequency deviation from your intended frequency of the peak of the boost factor would be. And you see the intended boost factor was something like well, 400 approximately, and the frequency deviation around 0 is 1 megahertz. So you see there is a stray, but it's not very dramatic. So this shows us that in principle, for a smaller proof of principle setup, the concept is feasible. Now we're still working on extending this, extrapolating this to many, many disks. So we believe the repeatability and accuracy of such a setup is a feasible thing. Now, obviously, what is extremely important is really to understand the booster response in terms of the signal, the reflectivity signal. So I told you so far we've been working with 1D simulations. Obviously, we need to understand the 3D effects. What is being done here at the moment is that we use a simplified dielectric haloscope, dielectric booster system with only 3 disks and a smaller diameter, 100 millimeter. Note, with going smaller in diameter, we have a massively enhanced effect of the boundary conditions, right? But now we can make a measurement, again, reflectivity measurement of such a setup and compare it to simulations. This is what you see up here. And basically, we see that all the peaks that we expect from basically our taper here, which is instead of the horn antenna that we used before, we expect many kind of taper peaks here. These are all reproduced in the simulation. And then we expect the main peak at a given frequency. Now, this is very nice because if we really understand our 3D simulation, we kind of have a calibration of our boost factor. Now, these measurements are ongoing, room temperature, and in a B field, this is work in progress. In February, we will actually have a first measurement of such a setup in the MORPURGO magnet at CERN in a magnetic field of 1.6 Tesla at room temperature. This is nothing dramatic, nothing really good, but looking into the numbers, I won't go into the details now about the sensitivity to GA gamma. Well, we will carve in a small frequency range with this setup into unexplored territory. So hopefully for the first time really being able then to have also for MADMAX a line in the plot. Also currently ongoing are liquid helium measurements in our labs in 2 kind of cryostats. So these are measurements currently being performed. I won't go into more details. Stay tuned here on this front. Okay, very quickly, the magnet, because this, of course, only works if we have a magnet. I told you 9 Tesla, 1.3 meter bore, and we rely on niobium titanium-based conductor. So these are the main challenges. First of all, we have to understand, is niobium titanium okay? Yes, this is okay. And now there are some questions, a potential showstopper. If we build such a magnet, can we protect it against quenches? Yeah. What are the peak fields in the outer areas inducing the forces? Are these fine enough? Very quick status report on that. On the main showstopper that we had in front of us, the quench protection, there have been measurements ongoing at Saclay, CEA very recently, using a test magnet that has been built by Bilfinger-Nöll. And these are very promising. There will be results soon being shown, but I can tell you we can go ahead with that. So we're very happy about that. Good. Now I'm frozen here, apparently. And my time is also going away. Okay, now I'm back, sorry. Then another thing I will quickly just tell you, the displacement of the disks. This requires special development of motors that have the precision and that can operate in 9 Tesla at 4 Kelvin. We are working together with JPE, a company in the Netherlands, and I can tell you We've built motors together with them, or they have built motors. We put them into cryogenic surrounding. As you see here, we tested them. We achieved a repeatability of better than 1 micrometer at room temperature, and we have operated them in 4.2 Kelvin, achieving a speed that is fine for us. Very soon this year still, we will operate this at a test magnet at DESY at 5 Tesla in a cold surrounding. Also, we're building a full-fledged prototype with just 1 disk and a mirror that also will be tested in magnetic field and at 4 Kelvin at CERN in the MORPURGO magnet and in a dedicated cryostat. I won't go further into that. My basically last slide. What do we hope to achieve with this MADMAX magnet if we're successful? And so far we have no real showstoppers. We should really be able to carve into this unexplored post-inflationary scenario territory with preamps up to 30 gigahertz. We can cover masses up to 120 microelectron volts or so what. Above that, in principle, the concept should still be feasible, but we need novel RF detection techniques that still need to be developed. Okay, I put you up my conclusions. You can read them yourselves. And sorry for taking 5 minutes longer than I should have. Thank you very much for your attention.
Thank you. Thank you very much. Thank you. That was a great presentation. Any questions? We have time for a couple of questions. Yes, Claudio, unmute yourself, please. Yeah.
Thank you. Hi, everybody. I have a question about the TWPA.
Okay.
Because I was just doing a simple calculation. Maybe it was wrong. It's early morning here, and but at your booster is at 4 Kelvin, right?
Correct.
So I think if my calculation was right, but I cannot assure it, that with 4 Kelvin in a, let's say, a 1 gigahertz bandwidth, you are close to the compression point of the TWPA. Is that right? Did you do that calculation? So you are almost saturating the amplifier in that case.
We did this calculation and it should be okay.
It should be okay?
Yes. Yeah. So we looked into that and we should be fine. You're correct. It's not trivial and we're close to saturation, but it should still be fine.
Okay.
Claudia, is this because of the large surface area? Is that what it is?
This is, I think it's because of the bandwidth of the temperature, but then I just did.
Yeah, right. It's the black body photon.
Right now the calculation, so maybe it was wrong. You know, you have to double check 3 times.
This is a great point. I'd like to see that actually. It's an excellent point. Yes. Brilliant.
It's an important point.
Thank you. Miko.
Hi, very interesting experiment. You mentioned that in the future you can go up to higher frequencies. So I guess my question is that what is kind of the highest frequency you can think about for this kind of measurement scheme?
Okay, that's an interesting and difficult question to answer. And this will very much depend on mechanical feasibility, right? I mean, if we go to higher frequencies, at the moment, the baseline design is for the lower frequencies, 20 gigahertz up to 30 gigahertz, that we can live with dielectric plates with 1 millimeter thickness, right? Obviously, going to higher frequencies, we would prefer to have even thinner disks. This obviously becomes more challenging to produce them. But there are ways around because we don't depend really on lambda half. We can also use 3 lambda halves or whatever within the disks. So there are possibilities to get around that. So in principle, what we always say is that the concept is feasible for axion masses 40 to 400 microelectron volts corresponding to 10 to 100 gigahertz, right? And in the end, what we believe is the showstopper is the distance, the lambda half distance between the surfaces of the plates, lambda half, right? And that basically determines the 100 gigahertz.
Okay. Well, yeah, I'm just thinking if the frequency is higher, would you actually make the plates then smaller? Like would I mean, because we would get more energy per photon, or is that too simple logic?
Well, I think I know what you understand, but look, this is it's about the density of axions in the universe as cold dark matter. So the power that you emit from the booster itself is actually constant. It's not dependent on the axion mass, the overall power.
Mm-hmm.
Okay, any other quick question this time? No, that was great, Bela. Thank you very much. That was absolutely great.
Thanks for your attention.